All right, let's go ahead and get started. So did we talk about what a basis was last time?
Yeah.
Trying to remember. Okay. So yeah, this basis, if I have a small set of vectors called B, and the set of vectors W is this much larger thing, which is a subspace, which is the span of B, then B is a basis of W. So if B is linearly independent and spans W, so those are the two conditions essentially. So now we've talked about this new structure, this new thing called a basis. Let's make some. So I'm giving you the small set of vectors, these three, and we want to find a basis for this subspace W. So any span of a set of vectors is going to be a subspace. So can we find a basis for this? So let's remind ourselves, what are my two conditions for a basis to be a basis? So I have to have linear independence, which I don't know if these three vectors are linearly independent. We got to do some investigation. But it also has to span W. I mean, so if I just wanted to make this linearly independent, I could just replace this by three vectors that I knew were linearly independent, call it done. But I have to make sure that it generates the vectors that I promise you it's going to generate. So knowing that those are the two conditions I have to meet, what are we doing with these three vectors? Maybe we should remind ourselves what the span of a set of vectors looks like, or what that's defined as. Someone give me a vector in this span. Yeah, any vector in this span. 114. Why is that in the span? So yeah, it's part of these three vectors. So these three vectors are in that span. Is there anything that's not listed there that's also in the span of S? Basically what I'm getting at is, how do we build up? So if I give you just a set of those three vectors, very, very small set of things, how do I build the span of S? So W is going to be a subspace that contains an infinite number of objects, an infinite number of vectors. But there's very specific ways that I can make those vectors. I'm kind of restricted to those. What are those restricted ways? Go ahead.
I'd say maybe adding vectors on scaling.
So adding and scaling on those, that's the complete list of things I'm allowed to do. So for example, I can just add the first two together. I get 2, -2, 6. And that just comes from adding the first two vectors in the space together. So basically, the span is all the linear combinations, that's the term we give to all the things that happen if I scale those vectors by multiplying them by any real number I can think of, and then adding all those things together. So that's what the span looks like. All right, so we want to find a basis for this. Is it possible there are three-dimensional vectors, or three-dimensional vectors that aren't in the span of this?
Yeah.
It's possible, right? It's also possible that this thing spans everything in 3 dimensions. So how can we find out which of those is the case? One of those two things is happening. So let's remind ourselves what linear combinations are here. So I have 3 vectors. So the way I can make any linear combination of them is to multiply the first vector by some constant, multiply the second vector by some constant, multiply the third vector by some constant. And then when I have those 3 arbitrary vectors, I can add those all together. So basically, I think of these like C1, C2, and C3 as these metaphorical dials. As soon as I make any adjustment to one of them, I get a brand new vector. And the full list of vectors I get from modifying those numbers, those constants, is the span. So what I'm going to do here, I'm going to rewrite this as 1, 1, negative 2, 1, negative 3, negative 1, 4, 2, 4, times C1, C2, C3. And I don't care what that equals. I just want it to equal something. Basically, I want to know what kinds of I just need it to equal something. I don't really care what it equals. I just want to know what vectors are going to, what can I make combinations of that are equivalent to using these 3 vectors? Because right now, I don't know if I have a basis. Because these 3 vectors, they clearly span something. If I give you any pile of vectors, they span something. But what do I not know? I don't know about linear independence. So how can I find out about linear independence? Find the determinant. So the determinant will just tell you yes or no. So if the answer is yes, then I think we can figure out what the basis, what a good basis is. Sorry. But that might not tell us what, yeah, I think we have to do something a little more careful to figure out what the basis would be. Yeah, we can, I think we just need to start reducing. So let's start doing that. So let's start that process. Let's get to reduced row echelon form. Start us off. Yes. So row 3 minus 4 of row 1 back to row 3. What direction did you say you wanted to go for the first one? Row 1 minus 2 or 2 minus 1? Okay. Row 2 minus row 1 back to row 1. What is this going to do for us? Okay. You're going to get a pivot in the top left entry. I think either I misheard you or I think this is what we should do. You may have said it correctly. I may have misheard you. But I think we're going to leave row 1 the same. 1, 1, negative 2. And we're going to use row 1 to alter both of the other rows. So what's the second row become? 0, minus 4, 1. And then 0, minus 2, 4 plus 8, 12. Do we agree? Okay. Cool. Got a pivot. Now what? Yep. So we can scale row 3. While we're at it, why don't we hit both? Or should we not? Now let me stop trying to help. Let's just do the thing you want. So negative 1 over 2 times row 3 to row 3. So all those numbers are certainly even. So 0, 1, -6, 0, -4, 1, 1, 1, -2. What's our goal right now? What are we trying to do? Right. So yeah, that's the like the big picture. But like, what's our like immediate next goal right now? What's that? Put a 1 where the -4 is. Cool. I see at least 2 ways to do that. What should we do? That's probably the most direct way, and that would certainly avoid any fractions. So I'm gonna transpose, or I shouldn't use that word. It already means something. I'm gonna switch 2 rows. Okay. We got a 1. So now we have our pivot in column 2. So what should we do about that? Cool. How can we do that? R2 minus row 1. Put that in row 1. And then I'll do 4 of row 2 plus row 3. Put that in row 3. So row 2 I have not done anything with. What does row 1 become? Ooh, I think I need to modify things a little bit. If I do row 2 minus row 1, that's gonna mess things up for me. Yeah, I think that's what we got. Row 1 minus row 2. So 1 minus 0 is 1. 1 minus 1 is 0. -2 minus -6 is 4. And then 4 of row 2 plus row 3, 0. 0. -23. I actually don't really care about that -23. All right, so now what should we do? Right, so that's easy enough. In fact, I'm just gonna do this because there's nothing else to worry about in that row. I have 2 non-zero entries, or sorry, I have 2 0 entries. The other one's non-zero. I can scale it freely. Is anybody seeing what's going to happen when we're fully done reducing this matrix? What's it going to look like? I'm going to get the identity. Now that I have 0, 0, 1 in that bottom row, I can hopefully we can envision the steps that it would take to remove that 4 and remove that -6. So where we're going to get here is 1, 0, 0, 0, 1, 0, 0, 0, 1. So we knew from the outset that these vectors spanned something. That's always going to happen. Like we don't know what the span is going to look like from the outset, but we know it's going to span something. It's going to span some subspace. Were these vectors linearly independent? We can now answer that question. The answer was yes. So we have at least 2 different bases we can talk about here. So now that we've gone through this reduction, I can tell you that this right here is a basis. Because whatever it spans is a subspace. And we just learned that because we were able to reduce it to the identity, it has to be linearly independent. So this is a basis. But what else is a basis? I'll call it S2. What else is a basis is this. Oh, I guess I should write these as columns. And really anything I've written, so if where we started was linearly independent, where we ended was linearly independent, That means that assuming we did everything correctly along the way, every matrix you wrote down was linearly independent. So basically, any 3x3 matrix I wrote down here is a basis. So that's one thing I wanted to bring up is that when we talk about a basis, it's never the basis of a matrix because they're not unique. You can always find a different one. But this one right here that we ended with, this right here is called the standard basis. Basically, it's a bunch of vectors whose only non-zero component is basically the first vector, its first component will be 1. The second vector, its second component will be 1, and so on. What three-dimensional vectors can I cover with this basis here? Literally every single one of them. Which means I can cover, which means the thing that this thing spans is R3. Which is not always guaranteed, but in this case, we just found out that these 3 vectors you can combine them to reach anything. So any questions here? Go ahead.
So for both linear independent and expanding.
Yeah. So, and just to kind of give you a counterexample, what would this look like what would our reduction have looked like if our initial set of vectors was not linearly independent? It wouldn't have fully reduced. So, like, let's. Hopefully that is clearly not linearly independent. If we started reducing that, what is something that would have to happen? You're going to have to get a row of zeros. It doesn't matter like how you start reducing. At some point, 1, 1, 1, and 1, 1, 1, those are the same pieces of information. So whatever work you start doing to cancel things out, you're going to wind up with a full row of zeros. So that row of zeros isn't also another dead giveaway that you have dependence. How are we doing? Okay. I'm going to throw a 4x4 at you. I might as well give us actual room. So we want to find a basis that spans W. So in general, the set of vectors I give you, it always spans something, and I'm already telling you the thing it spans is called W. So we don't really, when we talk about these 2 conditions for what a basis is, does it span some subspace? And is it linearly independent? You basically get this one for free. I don't know what the span is right now, but it spans something. But what we don't know is whether we have linear independence. So how do we find that out? Go ahead. Reduce it. I'm going to go ahead and actually, I'm not going to do what I said I was going to do. I don't feel like it's obviously legal. So 3 negative 102. And one thing I want to remind you of is the way we reduced that last matrix, when we got close to the end, we kind of took some liberties. We kind of said, all right, I see that it's going to reduce, so let's just write down the finish line. Now that we've reduced a bunch of these, we can kind of take the same kind of liberties. So if we notice certain consequences, we can, go ahead and shout them out. So how should we begin here? Go ahead. Now, once you add rows together, something got overwritten. Would you like to add row 2 and row 4? It feels like a good idea. Where do you want to put the result? In 4. So 3, -1, 0, 2. Zero, 2, -8, 0. Would it hurt anybody's feelings if I did this? All right, that's a good start. Now what should we do? What should we do? If we're reducing, what should our next milestone be? Get a 1 in the top row. So yeah, if we switch doesn't really matter which order we do this in, but I'll do, let's say negative row 2 goes back to row 2. And then I'll swap row 1 and row 2. That would do it, right? So 1, -3, 10, 3. And 3, -1, 0, 2. 0, -1, 3, 2. 0, 1, 4, 0. All right, we got a 1 there. We got most of the zeros underneath it. We just got to get rid of 1 more. So I'll do 3 of row 1. Nope, wrong way. Row 2 minus 3 of row 1. Back to row 2. Double check me. I feel pretty good about it, but the numbers got large, and that always makes me paranoid. All right, so now we got our first column's good. Now what? Eight of row 4 from row 2. Okay. Sure. So I'm sorry, what was the first thing you wanted to do?
We could, I guess, don't come top to bottom, I guess we could do it. We have row 4 to row 1.
Uh-huh.
We could also subtract 8 of row 4 from row 2.
Okay.
And add row 4 to row.
Okay, I can see now. Okay. So 3 of row 4 plus row 1 to row 1. -8 of row 4 plus row 2 to row 2. And row 3 plus row 4 to row 3. So that should clean up the entire column, right? So then I get 1, 0, 22. Three. And 0, 0. Oh.
Is there a reason why we lost the time of
Probably not a good reason. Which one?
It's like on the block.
The 22? There is no good reason. Did that hurt anything or?
Yeah, I think that's changed.
Cool, good. I like that 22. So let's make sure 3 times row 4, which is negative 12. I think it's negative 2, right? Okay. All right, that's better. But I also use that's got to be different. That's got to be 2, right?
That's what I'm talking about.
Oh, that's the one you're talking about. Okay, gotcha. And then negative 8, 0, so negative 7. And then row 3 plus row 4, 0, 0. I just flat out lost. Oh, no, I didn't. Here it is. Okay. I think that's good, right? Almost. It's one really minor thing we should do now, right? Yeah, put row 2 and row 4 in each other's places. I'm not going to rewrite all this stuff for that. Excellent. Now what? Row 4 plus row 3 and put that where? Okay. Am I being delusional about this space? Let's see. 1, 0. No, we're good. Row 3 plus row 4 gives me 0, 0, 1, negative 5. And then 0, 0, 2, negative 7. Row 1 plus row 4 and put that where? Okay. You caught it. Why is it a bad idea? It's got a 1. Yeah, it's going to undo something we've already done. But I think we're right to want to make both of those 2 zeros. So are there safer ways to get that done? Negative 2, row 3 plus row 4, back to row 4. So that gives me 0, 0, 0. Three? Okay. All right, now what should we do? Let's see.
No, it's positive.
Okay. What should we do now? Nah, I don't want to do that. I don't want to do any more reducing. Is it okay for us to not? Why is that okay? We got upper triangular, which means what? What did we learn? You can multiply the diagonals, that'll give you the determinant, right? I don't really need to know the determinant, so We've been reducing for so long, maybe we need to remind ourselves what the question was we were trying to answer. What were we trying to answer? Good. Is it linearly independent? Now that I have a pivot in every single column, could I conceivably reduce this down to the identity? Absolutely. Which means kind of same outcome as before. This is a basis for its span because it is linearly independent and it does span. I mean, this is going to sound weird the way I say it. This does span whatever the span of it is. And every set of vectors spans a subspace. But I think now we can say exactly what that subspace is. Or can we? Because based on what we're saying here, the end result of all of our reducing would be this 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, which means if you look at the columns of that identity, that's also a basis, those four vectors. What would those four vectors span? R4. So the span here again is basically the largest it could be. All the vectors of that many dimensions. How we doing? Okay. My last two for you. So now instead of talking about this generic subspace, this generic span, let's talk about this maximal thing, R3. Are these three vectors a basis for R3? First, let me ask is it possible for this to be a basis for R3? It's possible, right? But right now, so our two questions are always, is it linearly independent? And does it span, in this case, R3? I don't think I know either one of those yet. But we've talked about what we could do to answer that question, or at least the linear independent part. 0, 5, -4, -1, 1, 3. What's a good first move here? 1 plus right 3. So we already have a 0. If I add row 1 plus row 3, I get 0, 3, 3. Would it hurt your feelings if I did this? Now what? Go ahead.
I was wondering, sign up for Ocean Grant.
Oh yeah, you want to just cheat? Let's cheat. Let's get crazy. Did you reduce this? What's it reduced to? Oh, cool. So what does that mean? Clearly this is true, right? Does it span R3? The standard basis always spans whatever size, whatever the appropriate size of subspace it is. So we saw subspace in R4 in the last one. So last thing I want to ask you, is this a basis for R3? Oh, I got a yes and a no right away. Let's fight. So 2 questions. Is it linearly independent? Does it span R3? Well, if this spanned R3, then this better, because all I did was give you more tools. So it spans R3. Is it linearly independent? I got to vote for yes. Go ahead.
All of those, if you add like an extra form of variable,
Right, let me put it to you this way though. We just found out that these three vectors, if you can combine them, you can hit any vector in R3, right? Which includes this, which means it's not linearly independent. Because I have a column vector that I don't know what the combination is, but it must be a combination of the first three. Because I already proved through calculator cheating that these three vectors can be reduced to 1, 0, 0, 0, 1, 0, 0, 0, 1. So bases are not unique, but they all, if you have multiple bases for the same set of vectors, they all span the same thing. So these three things right here span R3, and so do, if I were to tear the columns out of that, that would also span R3. Which is why we answered this one for free. This spans R3, because there's no way I could add another vector that could span a smaller space. That can't happen. But it cannot be linearly independent. One more thing I don't know if I mentioned to you, but I've said several times today that a basis is not unique, but the dimension of a basis is. I don't think we've talked about what that means today. What is the dimension of a basis? What does that mean? The amount of vectors that are in it. So the dimension of this basis, so the dimension of S is what? 3. Which means that any basis you could think of for R3 has to have 3 vectors in it.
Again, what again does R3 represent?
R3 is basically all of 3-dimensional space. So when we talk about it in vector form, is all the vectors that look like this, X, Y, Z. So both the thing I circled and both the two things we circled, those are both bases for R3. I can make any vector you could possibly think of by combining vectors from either one of those sets. But that's one thing to keep note of, is that if you told me this 3-dimensional thing is a basis for R3, then there's no way this 4-dimensional thing can also be a basis for it. Because all bases for, if you have a subspace, all the bases for it have to be of the same size. They have to have the same dimension. How are we doing?
So it doesn't work strictly because
What do you mean it doesn't work? Right. So yeah, I'll answer this a couple ways. It can't be, so I've shown, since I found one basis for R3, that means I know what the dimension of all the bases is. Which means the fact that I'm even proposing a 4-dimensional basis is a non-starter. That can't be true. Specific to this, in example 3, I showed that, or we all showed that these 3 vectors span everything in R3, which means they span the thing I just added to it. So think about this linear independence. It's kind of like a lack of redundancy. So basically, I added a vector to this set, which didn't bring anything new to the span. So negative 1, 3, 2 depends on the other 3 somehow. We don't need to figure out how. We could, but it depends on the other 3 somehow. It's a combination. Go ahead. If they all had 4 rows, oh, it could be. So if you had like, 1, 2, 3, 4. Yeah. So any basis for R4 has 4 elements to it. No. So one thing that's not true is, so even though R3 is smaller than R4, R3 is not a subset of R4. So for example, 1, 2, 3 is a vector that lives in R3. 1, 2, 3, 4 is a vector that lives in R4. And even though they share a lot of things in common, these two things don't live in the same space. If this was 1, 2, 3, 0, now they're both in R4. They would be, but the fact that you're comparing a vector that only has 3 entries to a vector that only has 4 entries, or that it has 4 entries in it, they can't ever be equal. They're not even the same kind of object. If I can give you a metaphor, you're basically saying that a square and a cube are equal. A square makes up a cube, but I would not say that a square is part of. That's why I don't do metaphors, and they fall apart on me. Yeah, they don't have the same area, volume, whatever you want to think of. But so this 4-dimensional vector, let's go back to actually having them be different things. In the dimensions they share, I would say they're equal. I would say that V1 equals W1, V2 equals W2. But I can't compare W4 to anything because there's no corresponding thing over here. Okay. So the definition I gave of this R superscript n thing is that this is the set of vectors with exactly n entries, not up to n entries. And I think if you were to allow for that inequality, then you would also have to allow for the fact that you could have like a 2-dimensional basis for R4 or vice versa, which muddies things up in a lot of nasty ways. That's why they keep these. We're going to keep these things separate. 4-dimensional vectors and 3-dimensional vectors. There's a lot of ways in which they look similar, but we won't really compare them to each other. Does that make sense? Okay. I admit it's not something I've specifically thought about until right now. All right, let's put that one away. Let's see if I could switch to another slideshow without losing contact. Christmas miracle. All right. So now that we've talked about bases being these non-unique things, let's talk about this. Give me a basis for R3. Any basis you want. 1, 2, 3. I need more.
4, 5, 6.
Okay, are you sure you're making a basis? So remember we said a basis for R3 has to have 3 vectors in it, right? Because we found a basis and it had 3 vectors in it. I need a 3rd vector. Okay. Are we sure this spans R3? Are we sure it's linearly independent? How do you know? Did you already look at it? I think we've done this exact thing. So I don't think this is a basis, but we can think of one. Should we go back to the last slideshow? We made a bunch of them. One of them I called standard because it is the simplest. Yeah, here's a basis. This is a basis. Probably the most intuitive one. This is a basis for R3, right? If I were to use this, so basically with this basis, like think of this like with these like building blocks, these metaphorical building blocks, I can make any vector you want in R3. So if I wanted to make 2, -3, 6, how would what linear combination of those 3 vectors you gave me would I use to make 2, -3, 6. So let's call this V1, V2, V3. 2V1 minus 3V2 plus 6V3. And that's another reason with the standard basis is so useful. It's you can kind of pick out these constants very cleanly. But these constants right here, basically, I gave you the building blocks and you gave me the specific way to put them together to make a vector that I defined, right? Okay, so let's put some generality to this idea, this kind of like building up idea. So we're going to put more and more restriction on this idea of a basis. We're going to call it an ordered basis. So what do we mean by ordered basis? In general, the 3 vectors I just wrote down, it's also a basis, and it's the same basis if I just like switch 2 of the vectors, like if I just put them in different places. So the idea of an ordered basis, it matters where those vectors sit. So like these 2 bases right here, if I just call them a basis, these are the same. If I call them an ordered basis, they're now different. We good on that? New wrinkle, new definition for a basis. So if I make a vector out of a bunch of if I make a vector out of a bunch of like the generating vectors from an ordered basis, then I get all these constants, right? So C1, C2, all the way up through CK. 1 for every vector I have in my generating set of vectors. These things are called the coordinates. So in the metaphor that I was just kind of relying on, from those building blocks, the coordinates tell you how many of each one you need to make this generic vector V. So defining those coordinates from the standard basis is by design quite simple. Whatever the first coordinate is of the vector, that's how many of V1 you need. Whatever the second coordinate is, or second component is, that's how many of vector 2 you need, and so on. But not all bases are standard. Some of them are really weird looking. But it would still be nice if we could talk about how many of each one you need to make a certain vector. So that's kind of what we're going to do right now. Shall we? So I have a 3-dimensional vector, 11, -6, -12, and I have a basis, an ordered basis of something. I don't know what subspace is the basis of, but I'm telling you that 11, -6, 12 is in this span. So I would like to know basically how many of vector 4, 0, -3 and how many of vector -1, 2, 2 would I need to cobble together this 11, -6, 12. Any ideas how to go about that? Go ahead. That is eventually what we're going to do. Yeah, it's totally legal to do that. But let's talk about why it's legal to do that. So basically the question we're answering is this. I would like to know, all right, the only things I'm allowed to use are this building block and this building block, but I get as many of them as I want. But from whatever combination I wind up with, I want to arrive at this. So first of all, do we agree that's kind of what we're doing? Can I rewrite this in a way that's useful for us?
Did you make it so you keep them as a separate? Solid.
We're essentially going to do that, but we're going to do it. We're going to write it as a matrix that basically does that same thing. So let's kind of build up the matrix that I want to build up from scratch. So if I put this together, I put these two column vectors together as a 3x2 matrix, and I multiply it by C1, C2 as a column. Does that make sense? Yeah, okay. Basically, this is the equation I want to solve. So I have a 3x2 times a 2x1, and that equals a specific 3x1. But the way we've been expressing these things is as this augmented matrix. 4, -1, 0, 2, -3, 2, 11, -6, 12, -12. Does those augmented matrix look weird to anybody else? What's weird about it? You can't invert matrices like this. Um, the same as what? I'm sorry. Yeah, I mean that's what's going to happen here is that, you know, if I think about up here, if you can see where my cursor is, if I multiply each row by each column, I'm going to get so 4C1 minus C2 equals 11. Or 2C2 equals -6. Oh, maybe that's a dead giveaway. So all three of these different equations we've written down, one of them is not obviously an equation because it doesn't have an equal sign, but this really is an equation. It's a shortcut way to write one. They all say the same thing. They're all different ways of getting at, I want to know what C1 and C2 are. I think I can get C2 right now. -3, how'd you get that? Right, so if I rewrite these all as, let's actually write them all as different. So let's write it full algebraic. 4C1 minus C2 equals 11. 0C1 plus 2C2 equals -6. -3C1 plus 2C2 equals -12. So yeah, one of these equations just has a term that vanishes. So what does that look like in a matrix? Well, if I just make that middle row, if I cut it down by half, that says the same thing basically. Oh, okay. So row 3. Oh wait, sorry. Which rows do you want to deal with? Okay. Okay. Let's have like branching paths here. because really I don't care what order I get the information. So you wanted to add row 2 plus row 3 and put that back to row 3, Jack? Cool. So 4, -1, 11, 0, 2, -6, -3, 0, -18. Oh, that's right. I was not adding, subtraction. Which means this should be +3. We should wind up in the same place. All right, so I think from here we can call our job done. So what do we find out? What does C1 and C2 equal? 2, -3. Is there any danger involved with us answering this right now? There's a little bit of a risk. What's the risk? What did we base our C1 and C2 on? Right. So yeah, we dealt with some rows, right? But basically, I think we figured out what C2 equals from row 2. We figured out what C1 equals from row 3. We haven't really even considered yet what happens in row 1. We need to make sure that the constants we found agree with what row 1 does. So let's make sure it does. So here's the equation up here that we wrote for C1 and C2. 4 times 2 minus -3. What's that? All right, I feel good. So now I'm ready to declare this a good set of coordinates. If they don't agree, you can't really answer anything other than to say there are no such coordinates. That vector's outside of the span of that vector set. How are we feeling? Can we do one more, maybe, hopefully? Let me see what all I wanted to do here. Okay. Yeah, let's just stay on. All right. So now we're going to another vector. Another ordered basis. Okay, tell me how to get this thing started.
Would you do the C1 on the 5
Yep. So, I mean, in bottom line, this is the thing we're always trying to figure out. When I'm asking about the coordinates, by definition, what I'm asking is how many of each vector, or how many copies of each vector in this basis, in this ordered basis, do I need to make any vector that's inside its span? Specifically, the vector that I'm identifying here, this 6, 10, 7. So if I rewrite this as a matrix, I get 0, -3, 1, 5, -5, 5, -4, 1, 0, times C1, C2, C3. I need that to equal 6, 10, 7. And all those two equations I just wrote, those come from basically what the definition of coordinate is in this setting. So one last thing I'll do to rewrite this is as a augmented matrix. All right, so what should we do?
We do like couch.
What else do you want to do? Last time, so we didn't.
I know it worked out that way.
So we kind of did do Gaussian elimination. We can so in our last question, finding the inverse is something we could not have done. In this case, we can. We can try that. But some kind of matrix reduction, some kind of row reduction is called for. But I'll kind of remind you what's the thing we're trying to figure out here? We want the values of C1, C2, and C3. Once we get to a point where we feel like we can get them, we can kind of eject from the row reduction stuff. But right now, I think it's deeply non-obvious what any of those coefficients are, any of those coordinates. So what should we do first? Okay, and put that where? Row 2 plus row 3. Back to row 2. One, negative 4, 5, 17. All right. Good first move. Now what?
We can swap around.
Okay. Okay, we got a pivot. Now what?
One, three.
Is that okay? The numbers got really big, but really convenient at the same time. Go ahead and scale. I'm going to divide that row by negative 5. I think we're very close to almost there. Maybe one move away. I think adding row 2 and row 3 would be able to get us a constant right away. Where do you want to put that? Row 2 or row 3? Okay. Now what do we have? We got, so if I scale this row down to 1, 3, I got the C3 equals 3, right? And I get C1 and C2 from there. What's C2? C2 is equal to 6 minus 3, right? Over -3. So that's -1. And then C1 is equal to 17 minus 5 of C3. So minus 5 times 3 plus 4 of C2. So what's that, -2? So our coordinates are -2, -1, +3. Is there any need to check? So the last example we did, we had to make sure that we didn't have some kind of inconsistency. Do we have to make sure here? I don't think we do. Maybe we should if we have any doubt, but why can we get away from that this time? The first row. So the first row, basically, in this case, I have 3 equations for 3 unknowns, right? In this last example, I had how many equations, how many unknowns? 3 equations for 2 unknowns. I only need 2 equations to solve 2 unknowns, which is kind of what we did, right? We used 2 equations to solve for them, but there's a very real chance that first equation might say something totally different. So that's why we had the risk there. In this case, I think we dealt with all 3 equations simultaneously. So we really did. Maybe if we don't even we don't realize it, we did make that check. How we doing? All right. This is going to take a little bit too long for 3 minutes, so I'm going to go ahead and give you back some time in your day. I'll wish you a happy weekend.